Hello, I'm Luc Duponchel. I'm a retired mathematician programmer. For the moment I'm also cycling a lot and I'm also a gardener, but that doesn't matter too much. I'm going to present you a screencast about the Yoneda lemma. And in fact also an alternative Yoneda lemma which is appropriate for functional programming. I'm not the kind of guy who is thoroughly preparing screencasts, so expect me to fail, things can go wrong, but I'm going to present you all on the fly and hopefully at the end everything ends well. So let's start. What is Yoneda lemma? It's a fundamental result of category theory, and in a sense the Yoneda lemma is simple. What I mean is it's not complex. There aren't many concepts involved. It involves only three specifications: category, functor, and natural transformation. And it also involves two implementations of those specifications, namely the category of sets and functions and the so-called Yoneda functor. Moreover, all functors involved, including the Yoneda functor, are functors to the category of sets and functions. So we are not considering all kinds of functors. By the way, the simplicity of the Yoneda lemma doesn't imply in any way that the Yoneda lemma is easy. What I mean is, it's not. It's difficult. It's not kind of easy to prove. Another point is that the Yoneda lemma is pointful. It involves elements of sets. In fact, being pointful is the essence of the Yoneda lemma, and I'm not going to bother you with all the mathematical details, but it has been the inspiration to many mathematicians to look at the mathematics in another way than just the set theoretical one. I'm approaching all this in a very special way. I'm using programmatic notation. Our formulation and proof of the Yoneda lemma uses programmatic notation. More precisely, we use Scala code. There's one important implication of using programmatic notation. The class of objects is encoded as the set of Scala types, and elements of those sets are encoded as values of those types. Fortunately, it turns out that for the Yoneda lemma, this is not an issue at all. The proofs, which I'm going to show you, can easily, I would even say algorithmically, be translated to proofs that use mathematical notation. Of course, the specifications we are going to present come with laws, and they are encoded as lists of two values. The reason why I'm doing this is that it requires those values, the left-hand side of an equation. In fact, the laws are equational laws. The left-hand side and the right-hand side to have the same type, which kind of implies, at least syntactically, that they're also syntactically meaningful. Implementations of those specifications come with proofs, in fact proofs proving that they are satisfying laws, and they are also encoded as lists of values requiring that the values for all the proof steps, so all the expressions that are part of the proof, have the same type. And again, it turns out to be useful as far as kind of syntactically proving that the proofs are correct, and also semantically kind of giving confidence that they are semantically correct. So let's start. with our first specification, which is a specification of category, and I will keep on uncommenting things like this. Don't look at the green code. Here is the thing, and I also have another screen where I'm actually compiling everything. So, and you see this is automatically compiling code when I'm changing something, and it seems to be successful. The Scala compiler doesn't have any problem with what I'm doing. So what I did here is the following. The category specification for a binary type constructor C, binary type constructor parameter C to be more precise, declares two members, two def members. The first one is identity, and the other one is composition. So mathematically it means that there is such a thing like an identity morphism, and morphisms can be composed. So if I have a morphism from Z to Y and one from Y to X, this results in a morphism from Z to X. What I'm also doing is, just for convenience, adding a so-called extension that's Scala related for infix notation. So here this dot can be put between two morphisms to compose them, like mathematical people are used to do. And that will turn out to be notationally convenient instead of using these kind of expressions. By the way, just to be sure, it still compiles, you see, no problem. In what follows, category parameters will be named C, D, E, and so on. Of course, this specification, this category specification, come with laws, and here they are. I'm going to uncomment them. So suppose we have a category. That's how we encode that, and we make it explicitly available by summoning it. Then there is a left identity law, a right identity law, and an associativity law. I'm encoding those laws as tuples, again as lists, so that I'm sure, in fact, lists of two elements, so that I'm sure that the type system checks that they have the same type. So here is the first law. Don't worry too much about it, but I think it's kind of convenient to read. If I take any morphism, which I denote like this, I'm using a type full name, so Z to Y, and I compose it at the left with Y to Y. In this case, that's the identity. Then, of course, I get back Z to Y. That's the left identity law because Y to Y is at the left. Right identity law, same story. I'm just renaming the identity as Z to Z because it will be on the right now. Here it is on the right. And if I compose it on the right with Z to Y, then I get Z to Y. And not very surprisingly, an associativity law as well, which tells me that it doesn't matter where I put the braces. If I put the braces here or I put the braces here, it doesn't matter. Composition of morphisms is associative. Okay, so that was our first specification with the corresponding laws. Let's just see if I didn't do anything wrong. Okay, everything is successful. So let's go ahead and let's start with our second specification called functor. Right, so what's a functor? Well, now there are two categories involved. Let's call them C and D. By the way, I didn't mention that, but C is a binary type constructor parameter, D as well. I did mention that, but I did not mention, excuse me, the variance. But it means that just like functions, if you think about it, you're perfectly happy if functions with which require less and provide you with more, you will typically be perfectly happy with those functions. So if you pay less for a better car, well, you should be happy. And a functor is a instead of a binary parameter constructor, it's a type constructor parameter. It's a unary parameter constructor, and a functor comes with a function f, which, given a morphism from Z to I, transform for the first category, transforms it to a morphism in the second category from fz to fy. For all safety, okay, nothing wrong here. The so-called variance things here. So indeed, in this case, it's providing more by requiring less. And in this case, it's only providing more, or sometimes referred to as the Liskov substitution principle. Anyway, recall that f is a function. I will come to that later. Then we can define what an endofunctor is. It's an endofunctor is in fact a functor where only one category C is involved. The parameter names will be called f, g, h, and so on. And of course also functors come with laws, and here they are. If I have two functors C and D, two categories C and D, and a functor f, I make them explicit by summoning them. Then I have the identity law, which says that applying the functor to the identity yields the identity. So the identity of category C will map to the identity of category D. And the functor applied to the composition of two morphisms is the composition of the two applied functors. Okay. By the way, but you simply have to maybe look again at the video to get acquainted with it. All these things are type checked in this way. Let's see if the type checker actually is happening. Yes, the type checker is still happy. Okay, so that's our so-called second layer. And what's the third layer? Remember, there are only three concepts involved. The third one is a natural transformation. Just like functors involve two categories, natural transformations involve two functors. And here it is. natural transformation involving two similar functors, because they're both functors from the same source category to the same target category C and D, then I can naturally transform one to another by in this case it's a morphism. Remember that functors were functions, but in this case it's a morphism of the target category from Fz to Gz. There is another thing which is important here, and let's maybe go back to functor. I could go back to category as well, but the C, which is here part of this signature, okay, I'm talking about functor, so excuse me, it's actually the F which is part of the signature, is a parameter of the thing which is really telling that this trait, it's a Scala construct, is a so-called type class. The same with category, let's just show it. This thing here is a type class for binary type constructor parameter C. This is a type class for unary type constructor F. But for natural transformations, it's not the case. You know, there is no such thing like NT or T or whatever here. It's just, and now I'm talking object-oriented, it's just, instead of a type class, it's an object class. And for those who are mathematicians, don't think in this case about the object word as belonging to the realm of category theory. It's just the object world as belonging to the realm of object-oriented programming. It specifies objects that are natural transformations in the same way as you can specify objects that are functions or objects that are whatever things, cars, bank accounts or whatever. It's convenient to use Greek letters for them. And once again, also notice that this is a morphism of this target category, while this is a function. Another thing is that, just like before, like always, we can also say like, hey, I can define what an endo natural transformation is when only one category is involved. So, which means that only endofunctors are involved. Let's just double check. Yes, no problem here. Everything seems to compile fine. Okay, natural transformations also come with laws, in this case only one law, and it's a kind of commutativity law. So suppose we have two categories, two similar functors, f and g, and a transformation between them, a natural transformation. Don't worry too much about all these things, it's very verbose, but it's just to keep the Scala compiler happy. The most important is that we make them explicit by summoning them, and really the only thing you will have to read is this here. That if we first do functor G with a morphism, if we first do natural transformation throw and then functor G, it's the same as first doing functor F and natural transformation tau. By the way, the type system of Scala is kind of cool in the sense that, let's first see if this is okay. It is, right? And let's see that the natural transformations, they have a type parameter, okay? And so we go from z to y, so it looks as first we have to work with z. and then we have to, when we arrived at y, that we have to, that we're at y. And maybe you saw, just a second, that there is the IDE I'm working with has as an extension to do type checking, and it was taking some time before it could type check, but let's see what happens here. It was a little bit confused here, but eventually everything is okay. And that's the cool thing about using programmatic notation, is that you can be very concise, just like you would be when using mathematical notation. Maybe too concise, and if you're confused, you can actually let the type system help you a little bit. And in fact, maybe it can do that. Here you see actually the expression type above, that it involves z and y, and here you can also see what the expression type does. But anyway, I'm gonna show you a more compelling examples of this. So let's start with our first implementation. So we had our specifications, the only specifications that are needed for dealing with the Yoneda lemma, but of course the Yoneda lemma also dealt with the category of functions, an implementation. And so how are we encoding that? We are encoding that as a given. The function category where the identity just maps z to z, and composition of z to y and y to x. First the z to y and then y to x. Not surprisingly, this will be a category, and the fact that the definitions which I'm showing you now, which are definitions of the declaration of a category, that they are satisfying the laws, are left as an easy exercise. So we have a category implementation, and now the main functor implementation is the following. Oh, by the way, is everything okay? Yes, everything is okay. Is our famous Yoneda functor. The Yoneda functor actually is about composition. There's a little bit of a problem here. Yes, because I'm using special notation. So I'm first going to go to notation, and I'm going to uncomment what is here. And normally when I'm back here, it should be okay. And it should be okay here as well. Yes. So what is Yoneda functor? Well, given a category C and given an object, well, in this case a type, because you remember the types, the objects are types. Z, I can define a functor from the category C to that only category which I already have shown you, the functor category. Oh, it's away, but let's show it again. This famous functor category, category function. And so you can think about it as a function valued functor called Yoneda Z. Internally I'm even making it a little bit simpler, because the C and the Z are part of this thing, so I might as well abstract from it and call it YF. And so excuse me, the C. So it's actually a functor called YFZ, which maps a morphism from Y to X. duomorphism from y to x for the functor y of z. Okay, and what does it do? What does it do? If I have remember z is fixed. If I can go from y to x, so given the possibility to go from y to x, then I will map that to the composition of y to x with c to y to go from z to x. So going from y, well, actually going from z to y will enable me to go from z to x. Okay, so given y to x, going from z to y will enable me to go from z to x via by composing with y to x. Notice that this thing I could have written here instead of y of cx, I could have written c let's see what it was, zy. Okay, going from z to y, mapping going from z to y to z to x. That really doesn't matter. It really doesn't matter, and it's still a success, you see. But at a certain moment, we will really need those expressions, and the Scala language can actually use more complex expressions. But you see that it's a for those who knows about functional programming or mathematical logic, it's a kind of curried version. YF is a kind of curried version of C. So the point is that I really see that this is a functor. This is a functor as far as we look at the specification of functors. There I need something of z to something of y. In fact, I have to agree that in this case I go from y to x because z was already used. Alright, so that is the Yoneda functor. Recall that it's a functor from any category to the category of functions. So, where are we? We have enough machinery to start with our Yoneda functor lemma. Okay, so let's start. And let's see, maybe until here. Did I do everything okay? Yes, seems to compile. So yes, I don't need any more information. So what do I need? Well, my special notation. I need categories, functors, and natural transformations. I need my function category and the Yoneda functor, which I have explained. So I'm going to bundle everything in a class called Yoneda lemma, which involves this category, a fixed C, and then a functor. Not the functor like the Yoneda functor, but a general functor from the category to functions, to the function category. Remember, once again, I'm maybe going to go back to the Yoneda functor. The Yoneda functor was a functor from the category to function called Yoneda C. Okay, but in fact, in this case, I'm going to generalize this to a general functor G from C to function. Okay, and so we are going to present a lemma about it. And what does the Yoneda lemma states? For all categories C, all types Z, and all functors G. So C, Z, G, here they are. And all functors which are function value functors. So functions from C to function. There is a one-to-one correspondence between natural transformations of this Yoneda functor from this Yoneda functor to G. So there is a one-to-one correspondence to natural transformations from this Yoneda functor to this G. Well, I factored the Yoneda functor in, which is defined like this because it is just a type alias, and values of type GZ. So it kind of relates natural transformations with elements of sets. In this case, it relates natural transformations with values of types. Okay, so let's try to prove this. There's a lot of machinery that is used, so first of all I'm going to make my category available by summoning it. I'm using its identity. By the way, since that's just a detail, but for those who know about Scala and programming in general, because this was an extension, I don't need to import the extension, so this one I'm not using composition anyway. I'm defining this abbreviation YF, Yoneda functor. I'm also using this YF to just refer to the function of the Yoneda functor. The same G for the function of my more general functor. So the function of my more general functor. Okay, so what I'm going to do now, first, remember it was a correspondence between natural transformations and values. I'm first going to go from values not to natural transformations. So with every value of type GZ, I'm going to associate a natural transformation from YFZ to G, which is actually a natural transformation of function valued functors. How do I do that? By associating with GZ a natural transformation given though the actual morphism will first do apply a morphism to let's say if I apply that morphism from Z to Y to I apply the functor G to it, then it goes from GZ to GY, and if I apply it with to GZ, I will get a GY. So what does my Yoneda lemma 1 state? My first Yoneda lemma states that actually this is a natural transformation, so that the commutativity law is satisfied. So, and that's actually what is written here. If I first do YF of Y to X and do the transformation, it's the same as doing first a transformation and then G. So it's a natural transformation between Yoneda functor and G. Okay, let's just for all safety check everything is fine. Yes, everything is fine. And again, and in this case the types are different, but let's just be a little bit, try to be dangerous. Let's see, I guess this will then be an X, and this will then be a Y. Yes, I guess so. Is that true? No, from y to x, yes, and y. Let's see. Yes, everything is fine. Okay. Well, at a certain moment, so that's because I was typing and it was actually compiling while I was typing, which is okay. So you see, and again, in this case, it's simple because, you know, I go from y to x, and then here I'm with an x, and I didn't do anything, but afterwards I go from a y to an x. So that's simple, but believe me, sometimes the type system of Scala, and that's really what has helped me a lot, can help you with doing silly mistakes. Okay, so if I have an element of GZ and I do define this natural transformation, mapping a morphism Z to Y to this thing, then actually it is a natural transformation. Let's prove it, and that's our first proof. And let's do it as follows. Hop. That's how we are going to do that. I guess that everything will be okay, yes. So I'm simply putting the left-hand side above and the right-hand side below, okay? And I'm going to try to find out what I can do. I will always work from the bottom to the top. So here is my thing, and of course, proving that those things are the same means that they react in the same way to functions of Z to Y. So I'm actually throwing in an extra function from Z to Y. But that a function from Z to Y is actually this thing here. Remember that is the same as, a morphism, excuse me, from Z to Y. So I'm what am I doing? Yes, I'm again defining my YF to G as transforming my transformed element. Here we go. So a first step. What is the first step? And so I'm going to do many of those. Is that I can use this thing, the definition of composition for function category. So that's simply replacing, okay, this is composition of two functions. Remember that functors are functions, and I'm just applying that. Now you can say like, hey, how can you use this? Because, well, the very reason why I can do this because I explicitly, imported function category, the function category implementation, so that I can use the general morphism composition for function composition. So yes, that's the first step. Then I can use the definition of the Yoneda functor, and it's actually very simple, really. Yoneda functor of yx and zy is just yx composed with zy. Right? That's really that. It's a curried version of composition, so to speak. Just to double check, believe me, it still works, okay? Well, it still compiles. And in fact, for how would I say, generic propositions like Yoneda lemma, the fact that they are syntactically correct give you some confidence that they are syntactically correct as well. In fact, it's the opposite. If something goes wrong syntactically, you probably did something wrong semantically as well. Okay, so now my actual definition of YF2G, I'm just substituting the definition for what it is. just literally what it is. So that's it. Then the definition of this function here. Believe me, that's just this thing. So it is just the g of that thing applied to gz. Remember, it was converting an element to a natural transformation. Now I have a functor which is composed, which is applied to the composition of two morphisms, so I can apply the functor composition law, right? Again, I can apply the definition of composition for the functor category. And the funny thing is now that at this level I can also use my value to natural transformation definition again. It's just this thing. So I don't even worry about, I don't care about what is standing here. And again, I have my YF2G definition in terms of V2 and T. And we're done. Because now again we can also use the definition of composition in the functor category. We heavily used composition in functor category 1, 2, 3 times, or maybe more, but okay, my proof is done. So yes, if I have a value of type gz, I can associate with it a natural transformation from the Yoneda functor of z to g. What about the opposite? Oh, let's just double check. Is everything okay? Yes, everything is okay. As far as the type system is concerned. So let's go the other way around. If I have a natural transformation, how can I then extract a value from it? So how can I go from a natural transformation from the Yoneda functor to a value of type gz? Well, that's relatively simple. I just apply it. It seems to work by just applying it to the identity. In this case, the identity from z to z, right? So I could write here, well, but it doesn't matter too much, but because it's all verbose and the Scala type system can infer things. So why would I write it if it's written here as well, and here again? So I might as well use identity. Okay, so it still works, but I might as well get rid of it. And what is the second lemma is that, well, here we are now saying that if, okay, that's true, I have associated, remember I've associated with a value natural transformation, now I have associated with a natural transformation value. What if you do both? Well, if you do both, it should come back to the same. So if I first do go from a natural transformation to a value, and then from a value to a natural transformation, it would make sense to actually have the same natural transformation, right? So how are we going to prove this? As follows. always the same thing. It's a list of things. Oh, yeah, have a look at it. I wouldn't be surprised if I don't need this type annotation. Voilà. Sorry, can I just correct this here as well? So in fact I don't need it here. This is my readme file. I can correct it here as well, so I might as well do it now. Okay. Okay, so it's the same trick. I'm going to work upwards. So here it is. I'm saying it's the same natural transformation, so this means that if I go to the tau of it, which is actually the corresponding morphism, and I apply it to z to I, it would be 2 times the same. Okay, so this one and this one needs to be the same. So let's go ahead and let's apply value to natural transformation, and the value to natural transformation is the one we already had before, which was this one. So the g of the thing applied to the value. So it's a g of the thing applied to the value. And the value itself is still an nt to v, so let's do that one again. And that was actually applying the natural transformation to identity. It's almost mechanically, right? And you see there's no problem, the type system is perfectly happy with it. Okay, so now we are at the stage that, so remember we are in the world of functions now, that we can use the definition of composition for a function category. And now, remember that we started with the natural transformation, so in the previous proof we proved that starting from a value we had a natural transformation. Now we start from a natural transformation, so we can use the natural transformation law to actually swap the transformation from left to right, right? So the natural transformation between yf and g. Again, we are going to use function composition for functions. And now we are also using the definition of the Yoneda functor, which is, like I said, the Yoneda functor of some morphism, and some morphism is just this morphism after this morphism. It's just a current way of writing morphism composition, and hey, identity. So if I'm actually composing a morphism at the right with the identity, I might as well not do it, and here we go. So we have proved that at least in one direction, first from a natural transformation to a value, and now from a value to a natural transformation, gives me the same result. We also have to prove the opposite, but let's just first check if we didn't do any stupid things. Everything is successful. Okay. So that's our third lemma, which is the other direction. Suppose we start with an element, turn it into a natural transformation, and go back to the element. GZ, it should be GZ, right? The proof is even simpler. That's really a simple proof. And I'm not going to go into all the details with commenting out. Let's start with this. Okay, let's start with the definition natural transformation to value. Remember, applying to identity. Remember first the functor applied to the element, which is this. In this case, it's apparent that we here have CG identity. Remember that G was a function valued functor, so it's actually the function category identity, which is just the identity function, and the identity function applied to GZ is trivial using function application GZ. And we're done. So what did we actually prove? We proved that indeed there is a one-to-one correspondence between, on the one hand, values of type GZ and natural transformations between function-valued functors. Natural transformation between the Yoneda functor, which is a function-valued functor, and the functors function-valued functors G. This is a very deep result in category theory, but we want to go one step further and try to see if something can be done in the realm of functional programming. So basically in the Yoneda lemma is about functors from a category to the category of functions, but functional programming deals with categories where I have a functor from functions to the category. So because we want to treat functions as morphisms, and we do that using a functor from the category of functions to the category. And so if we compose them, first go from the category to functions and then from functions to the category, we have an endofunctor. So it looks as if we are dealing with endofunctors. So the categories which I'm referring to now will be called functional categories, and for those functional categories we have a Yoneda lemma for endofunctors instead of a Yoneda lemma for function-valued functors. For endofunctors instead of function-valued functors. The second thing here is that it looks as if the category of functions somehow disappeared. It was just in the middle of this composition of two functors. First we went from our category to functions and then from functions to our category. So it makes sense to make that, to make that proposition or that lemma and its proof point free. So not involving any elements of sets, and if you think about it programmatically, not to involve any values of types. And that's exactly what we are going to do. From a syntactical point of view, from a complexity point of view, our Yoneda lemma will still be simple. It needs only two extra specifications, a triple. We need to know what a triple is, and we need to know what a functional category is. It will be some extension of a category involving triples. And of course one extra functor implementation, which will be our Yoneda endofunctor, which I already referred to, the composition of the normal Yoneda functor with then that functor from functions to our category. And like I said, functional categories, perhaps not surprisingly, model functional programming, and everything will be point free. Of course, we will need a replacement of elements, and the replacement of elements will be so-called global elements. But remember, global elements will be morphisms. So I will only talk about morphisms, no objects. In the case of Yoneda lemma, elements of sets, or in our case when we work programmatically, values of types will be involved. It will all be point free. So let's start with triples. What is a triple? Here it is. And let's just for the moment only uncomment this. Does it compile? Okay. Again, notation question. I agree. I need the composition of functors and I need an identity functor. So I need this here. This is actually, this I will be notation for the identity functor. I actually not going to use the identity functor yet. I'm going to, don't need it yet. And the same also for the composition of functors. I actually don't need the functor composition implementation yet, but I need it for notational purposes. And I wouldn't be surprised that now it's okay. Yes, it's okay. All right. So what's a triple? Okay, a triple T is an endofunctor of a category. So given a category, it's an endofunctor, which I conveniently call T because of the name triple. And it has two natural transformations. Endo-natural transformation, because from now on we are going to talk about endofunctors. Only one category will be involved. From the identity to T, so from 0 times T to 1 times T, think about it as such. And there will be another one called mu. They are referred to Greek letters, of course. From T composed with T to T, so from 2 times T to T. Right? The actual morphism, so the tau morphism, I will denote them by Greek letters nu and mu. The N stands for neutral, the M stands for multiplication. More about that later. So it looks, to a certain extent, we are thinking about a multiplication-like thing here with a neutral element. I'm making this endofunctor explicit. I could have encoded it differently, but so that's my endofunctor, which I make explicit because I need it later on. But I will definitely lead my function from CZY to CTZTY, which is actually this one. I could actually have called this, and I'm going to change that one. Control copy. Voila, this will still work, see? And let's go to the README file, because then I can, here it is, and I could as well, here it is already, it's already changed, okay, no problem. So my documentation was okay, but my code wasn't okay. So a triple has these two natural transformations, and the Scala, even though I didn't talk about functor composition in the identity functor, the Scala type system is perfectly happy with this for the moment, but it will need them later. And so again, they come with laws. And what are those laws? And they're actually extremely simple. I've put some things in comments, but don't look at the things that are in comments. Here it is. Now I need an identity functor. I even need an identity natural transformation. So I will make them explicit. And where are they? Their implementations. Identity endofunctor. And identity endo-natural transformation. Really completely trivial things. They just do nothing. Right? They are just, both are the identity basically. And hopefully everything will be fine now. Yes. So if I really go into the this was just syntax. This is just syntax. Specifications are syntax, and this is semantics. Then I really need to refer to things that exist. I make my triple explicit by summing it. I also it's just a matter of notation. The identity functor f, I call it normal letter, and the transformation I call it iota, which is the Greek one. Okay, I also have to make this one available somewhere. It's needed. I don't know where, but anyway, it should be. Yes, it's available as a given. It's Scala technical thing, but really it's needed. Suppose I don't do that, and that's actually funny. If I don't do that, oh sorry, Control Z. Alright, come on. That's what I should do. Then it will probably complain. Well, here it is. Oh, it doesn't, sorry. What am I doing? Not found type T. It doesn't complain for the moment, which is kind of cool. So maybe it's not really needed. Okay, if it's not really needed, then I'll just do it away. I will do that away later. Oh, okay. Don't worry. Okay. So that's good news. So I don't need it to be deleted. I will do that later on. I guess I need it because it's a simplification of some code that I've used before. So for this specific code, it's not needed. Okay, so I have my triple, and I'm importing the t, the nu, and the mu. First of all, I have the two commutativity laws because remember they were natural transformations. They were natural transformations, so endo-natural transformations. I just translated them. So you see it's the swapping of the natural transformation from left to right. Here the swapping of the natural transformation from left to right. Here 1t, 2t's, 1t, 0t's. But this is another one, the left identity law. So it looks as if I first do nu and then do mu, it's the identity. Or if I first do nu and then do mu, it's the identity. But look, there is a t here, I will talk about it later. And then an associativity law, which is if once again I first do the t, mu and a mu, it's the same as a mu and a mu. It's a kind of strange thing, but look, there are three t's involved here, and there might be some associativity involved to this, namely, well, maybe this one. Oh, sorry for that. Where is it? Maybe this way of associating, okay, or the other way of associating, and it's related to that. Or the other way of associating, it's related to that. And how is it related to that? Because we have kind of three layers of t's. And look now, I can, well, in fact, and that's really nice, the type system gives me some hint here. If I look at this here, it goes from tz to ttz, but in fact it's supposed to go from z to tz, which means that it is actually this. And this should be also be list. It should actually be this. And this should actually, well, that doesn't matter too much. This. Control Z. And this one should actually be did. Yeah, it's a list, eh? Which, in fact, I'm going to write triple O's, Control find. I'm going to look if in my README file I also use the right notation, triple O's, here the right, list, and I think, what did I do, commutativity, yes, here I already changed them to lists, okay, good. So back to here, and back to here. Now, for those who are inclined, those who know a little bit about mathematics, now it's more symmetrical because You know, the left thing, mu is on the left, well, I don't care. Or you could also say that, well, it depends on what you mean by left and right. You know, maybe I should do it in a different way. In fact, here the mu is, here the t is on the left, sorry, the mu is on the left, and here the mu is on the right. Okay, you could also concentrate on the t. But you see here mu t, and here you see t mu. And what's really involved technically is that functors are composed with natural transformations here. And here also, functors are composed with natural transformations on the left and on the right, and it doesn't matter. So this is here refers to a kind of identity thing, and this refers to a kind of associativity thing, because remember here treaties are involved. It's technical, but it's kind of funny, and even more important, it's very kind of powerful that as far as Scala's type system is concerned, let me just see first of all if it's okay, everything is okay. As far as Scala's type system is involved, it doesn't matter if you just use the type annotation or not. And that's really fantastic, in my opinion. Sometimes in mathematical notation they are too verbose, and sometimes in mathematical notation they are not verbose enough. Here it doesn't matter too much. The most important thing is you can't fool the type system. Okay? And more important, the type system help you. Once again, here the mu is going from tz to ttz, and here the mu is going to from z to tz, you see? And it's the first argument. The first one is the identity, so here you use the z, and here you use the tz. Okay? Cool. Well, apart from that, maybe a little bit too exciting, too much excitement, we are going to continue with our explanation. And remember that we have along the way introduced the identity endofunctor and the identity natural transformation, which are both completely trivial, satisfy the laws, but we are not going to go into the details of that. So let's now continue with what is a functional category. Functional category is an extension of a category where triples are involved. First of all, it looks as if I need a Yoneda endofunctor, and it looks as if I need extra notation, so let's introduce that extra notation first. I need, well, a type U, which is a type unit, which is a singleton type. It's a kind of final type. It's like a singleton set with one element, and it will be used later to define what I will refer to as global elements. But we are not done yet, because I need the Yoneda endofunctor. It's actually the definition which I'm giving here is mutually recursive with the Yoneda endofunctor, but I will look at the Yoneda endofunctor later. And first at this here. But now I guess that everything will be okay. Yes. Oh, not everything okay. Compose. Okay, very good. Yes, indeed. The Yoneda endofunctor, by the way, is a composed functor. Remember, it was a composed functor first from C to function, and now from function to C. And I need indeed the instance of a composed functor. And that's also really nice that the Scala type system just suggests me what I need. Well, of course I did already implement it, but I uncommented it. So yes, you need, for defining the Yoneda endofunctor this way, you need to know that the composition of two functors is a functor. This can be done away, and this. And now I think I'm done as far as the type checker of the type inferencer in this case is involved. So yes, I have a functor from, in this case, from the category to from functions to C, which doesn't do anything with the type. So really a function from A to B will be mapped to a morphism from A to B. There is no shape changing involved. And that's a nice thing, we also say that, and this will turn out to be the global functions, because that's actually Yoneda CU. I'm not going to go into detail. I'm not going to change that to another alternative where it's apparent that we are talking about morphisms here. But think about it as, and in fact I make it explicitly here, CUI, or I could also have written Yoneda I could also have written here Yoneda CUI, I guess, see, and in fact it still compiles. Voila. But let's just write it like it was, because I've already before. Okay. So here is the Yoneda CU, you see, this will be what I call my global functor. So we are going to introduce global elements which are simply morphisms from U to Y. So a global element of type Y is just a morphism from U to Y. Remember that U was a synonym of this singleton type. So again, two things here. We need functions to be morphisms, and we need global elements to form a triple. That's what it means in normal words. Okay, so function category is also a convenient place to define some synonyms. F2M, function to morphism, is just the function that maps a function to a morphism. GF, like I said, was my global functor, and GF in lowercase is actually also mapping a morphism from Y to X to a morphism from global Y to a global X, because it's simple. If I can go from Y to X, then going from U to Y can be transformed to going from U to X. Another interesting one is value to global value, and because functions are first-class citizens now, so to speak, using F2M, everything which I can code as a function can also be more or less encoded as a morphism, which we will see in a moment. But this thing here, value to global value, is just a function that, given a z, lifts, or so to speak, the function, the constant function from u to z to a morphism. So it goes from a value to a global value. And finally, I can even lift that one to a morphism. Okay, and it's actually a morphism from the identity functor to the global functor by just once again using F2M. So I'm using F2M twice. What you see, actually, I said I declare function category as being telling that the global functor is a triple. I was actually even able to define the new transformation, endonatural transformation from the identity to GF. I'm not able actually to define the one from twice GF to GF, That's something that you have to do for every specific functional category instance or implementation. And there is one extra law, which is the so-called new law. By the way, when thinking about triples and also about functional categories, because they are fact, they are also triples. Triples, the neutral element, kind of, how would I say, introduces a T layer around a Z, and the mu kind of removes a T layer. Okay, see? And so they are kind of the inverse of one another. And as far as functional categories are concerned, remember that the functor we are talking about is the global functor. Then the new kind of introduce a global layer, and the mu, the multiplication, removes a global layer. Think about it. Now, so once again, the nu and its corresponding nu in Greek letters introduces a global layer. And so what is this new law? Well, there are two ways of introducing such a layer. First of all, by using v2gv, by using this function value to global value. But if you already have a layer, so if you already have a morphism from u to z, you can also do that by composing with nu, because you can go from u to z and then from z to, well, UUZ, so to speak, 2 times. See, my global functional layer. And it's kind of natural to assume that both are the same, so that composing with this endo-natural transformation morphism is the same as value to global value. So that's my actual functional category law. So what's next? I can start already with my main lemma, which is now called my Yoneda lemma. And let's just uncomment a few things. Remember that the Yoneda lemma was about the correspondence between elements and natural transformations. We will still have a lemma about elements and natural transformations, well, more precisely global elements, or even global elements, 2 layers. But before doing that, we're also going to do some, like always, formulate and prove some auxiliary properties. So a lot of boilerplate what is needed. So if I have my functional category and I have an endofunctor and a z, and remember it's about functional categories, I will still need a z an element. So it's really okay, to a certain extent there are still elements involved, but we will see that we are not going to use elements, we are only going to use the type. And I have now an endofunctor. So you see the function category doesn't play an explicit role anymore. I make it available, and I still need it, but it's not explicitly needed. I need the functional category artifacts. I import them. I use the same synonyms and so on, blah, blah, blah. I borrow them from the Yoneda functor and the Yoneda endofunctor. My endofunctor is called lower G, I still need my identity natural transformation and so on. Don't worry about it. But now we had a new law, but we can actually prove a mu property. We can prove a property of mu which uses the new law. And what is that mu property? Well, again, suppose I already have two layers. You see, two global layers. Then I can do two things. I can add a third one. I can add the third one, value to global value, and then I can do one layer away using the mu. See? And remember that the associativity of functor composition didn't play a role. How I do it away, I don't care. But that's the thing is that I first add one and do it away, then I probably should end up with the same thing. And that's actually what its mu law is all about. And this mu property is all about, and we can actually prove it. So, like always, let's start with our two things, one on the top and the other one here. Well, I am going to use the category right identity law, because remember that this thing is here. If you look at it carefully, the identity natural transformation is just the identity morphism of the category, so I can put it on the right. Category right identity law. Then, now here's the thing. I'm going to use my triple laws now, namely this one. Remember that one of the triple laws was that if I do I guess I have to did I make a mistake? It should be like this, eh? What am I doing here? Sorry for that. Okay, I think I should do this, and hopefully it's okay. I should do this, right? It should be here. So, once again, sorry for correcting my... I'm going to do that here as well, in my README file. Why not, eh? So I should actually do it like this, eh? How did I define it? Shit. Okay, I'm going to copy paste. So you see, you can see me fail, but on the other hand, that's natural. Failing is natural. Okay, so let me just double check it. Everything is okay. Well, it seems to be okay, right? That's the good news. So my natural transformation was on the wrong part, so right. Left, so I just switched left and right, okay? Not a big deal, but we have to be correct. Alright, here it is. So indeed, this was the triple, it could be the triple left one, I don't know anymore. Okay, so now I see it. It's actually, yes, okay. The point is that I'm using the category left identity law. No, okay, oh, sorry for that, left. And probably this is the right one. Okay, let's just double check. Why not? Triple mu is the left. So did I do it right? Then I should actually do it again. That should be left. Oh, both are left. Okay, don't worry, left. So you see, that's the one of the category and that's the one of the triple. So this should also be left. Okay. Right. Right, here we are. And so that's his thing here. And then the functional category new law, that's a nice one. That this thing is the same as this thing. And we are done. Okay? So the mu property follows from the new law. Nice. Cool. Another thing, well, since we are working in point free, you can expect that maybe some things that you're used to do point full can also be done point free. And in fact, you can think of function application being defined in a point free way. Okay, everything is green. So what is this thing here? If I have my function application here and I make it turn it into a global value, then I might as well turn the argument into a global value and compose it with the corresponding morphism. Alright? That's what this thing here is doing. It's actually a kind of, and here again, I'm pretty sure that I don't need those things here. And in the README file, I think it's by not doing it here. Pointfree application definition, I don't need it here as well. So why not doing it? Wow. Okay. Alright, just double check if I didn't do okay. So, that's called point-free function application. It's a point-free version of function application, replacing elements by global elements, replacing this element by this global element, and replacing application by composition, right? And again, easy to prove. Let's start here. Let's just use the definition of V to value to global value, the definition of composition of the function category, the functor composition law, very important, and then again we have again our global value, and that's it. Another thing is, well, remember that the Yoneda functor is about composition, and we can also define the Yoneda functor in a completely point-free way, in the sense that if I have the value to value of the composition of two morphisms, so I have and remember here that it's important to understand here, and that's a good example, that morphisms are values, okay, in our setting here. It's the beginning of they are kind of partially closed categories, or whatever they're called. Morphisms are internal, they are objects, they are values. Anyway, if I make that composition of those two morphisms global, I might as well first make the first one global, and then compose it with my Yoneda endofunctor. So again, it's an interesting property that can easily be proved. Believe me, I first use my function application, which I just proved before. I have to be a little bit careful here with typing information. It doesn't happen a lot. But if I don't give the right typing information here, the type checker complains, and it complains here as well. See? So this is one of the rare occasions where we have to use a type inferencer. Then in fact I'm using the normal Yoneda functor, which is the composition, which is is doing the composition, and then I'm using the Yoneda endofunctor, because remember that was the composition of the Yoneda functor with the mapping from functions to morphisms, and we are done. Believe me, that's how it works. Okay, now we are going to proceed along the same lines as with the, now that we have our auxiliary propositions, we are going to proceed along the same lines, but it will be slightly different. What we are going to, what the lemma is all about is the following. The lemma states that for all functional categories, not normal categories, the functional categories, all types Z and endofunctors G. So we are talking about types Z and endofunctors G. There is a one-to-one correspondence between endonatural transformations from the Yoneda endofunctor to no, not G, but GF followed by G. So these endonatural transformations and values of type this here. So the correspondence will now be between endonatural transformations of the Yoneda endofunctor from the Yoneda endofunctor of Z to GF, the global functor composed with G, and global values of type G, of type C. Okay. For the normal Yoneda functor, this GF would not be here, and those two GFs wouldn't be there either. Okay. But of course, you see there is a GF that somehow is introduced maybe by nu, and there are two GFs maybe that are related to mu. By the way, now I see that in my here there should be Yoneda endofunctor. Okay, right. In my README file. So let's first try to find out how do we go from such a global value to an endonatural transformation. It's very similar. We are actually going to apply the functor composed with GF to Z to I. That's what we did before. And compose it with our global, not apply it, but compose it with our global value. Turn it into a morphism and then apply mu, because we actually have one layer too much. It's a kind of generalization of what we did before. So that will be our way of going from a global value to an endonatural transformation. From the Yoneda endofunctor to GF, global G, so to speak, the global G functor. Again, I have to prove that it is a natural transformation, so I state that lemma, that it's a natural transformation, right? And so here I do my transformation, and you see indeed that the Yoneda endofunctor should actually commute with GF to G, and there is a proof. So it's a longer proof, you see? It's a longer proof. I'm going to go over it relatively quickly because so many things are involved, but believe me, it just works. I'm using my pointfree Yoneda functor definition, so I'm switching from using that proposition which I've just used before, which will actually, well, this thing here you see global GF global value thing, it's here that it happens. It's just the global value of this thing, okay? My definition of the thing here, just copy paste. Believe me, again, the definition of my global value to NT. Believe me, it's okay. You can take your time and have a look at it. It's just expression substitution. Again, I need some help from type system, but in fact it makes sense here because I have my value to global value, and here I go from z to y, and then from y to x, which means I'm actually going from z to x. So it makes sense that this is a z to x. And again, believe me, the type system, the type inference system has helped me a lot by finding out the right expressions. Here I'm using my mu property, which actually is a consequence of the new property, which extremely simplifies what I'm doing, because you see the thing becomes much simpler. It's the mu and value to global value just disappears, basically. Here I'm in a situation where I have a functor, namely the composition of the global functor in G applied to a composition of two morphisms, so I can use functor composition. I can apply my mu property again to this part. I can again do my point-free application. Now I can do so in the opposite direction, my point-free application definition. Complex expressions, believe me, but that's exactly how it works. And then I also go back by using so it's actually in the other way, almost in the other direction as I did before, and the definition of things. So you see, it's all, the trick is that I actually kind of unwrap and then wrap it again. But using the mu property as the basic property to change something somewhere. Believe me, it just works. And you can have some time to look at it later. So it's the most important is the idea that values are replaced by global values, and the function valued functors are replaced by endofunctors, and the natural transformations are replaced. So from the Yoneda functor to a functor are replaced by the Yoneda endofunctor to the global functor composed with a functor. So let's go the other way around. How do I go from an endo-natural transformation from the Yoneda endofunctor to the global functor composed with that endofunctor, and how do I turn that into a global value? Well, again, maybe you recall that the identity was involved in the Yoneda lemma, in the Yoneda endo lemma. Of course, it will also be involved. Turn it into a global value and compose it with my natural transformation. Okay, let's just go back to to show you how you go from the point full world to the point free world. If I look at this here, it's actually just the natural transformation applying to the identity. Here it's the natural transformation composed with, well, not the identity because that doesn't work, but the global version of the identity. So it's always kind of turning application into composition and stuff like that. And then I have my other lemma, which says that, okay, if I first do one and then the other, it wouldn't matter, okay, with a proof. And I also have this one, if I start with a global element, first turn into a natural transformation and then go back to the global element, it shouldn't matter as well, okay? And both have a proof. If you don't mind, I'm not going to go in all the details, but it's always the same stuff, just using the two definitions. Point-free application definition, my mu property. Remember that in this case we were starting with a natural transformation, so I better use it. So here I'm using my natural transformation commutativity law. I also use my point-free Yoneda functor definition and the category right identity law. Believe me, the proofs are kind of similar. They are very similar. That you see category right identity law, you see it, category right identity law. I will probably also use the Yoneda definition of the Yoneda functor. You see, here I'm using the definition of the point-free Yoneda definition of a point-free Yoneda functor definition proposition. So it's more or less the same thing. And the same for this thing here. All right. Again, okay, let's just see. I'm using my two definitions. Here I'm using my two definitions. There is some identity law, probably here as well. Here it is. But before doing that, I first do my application things to be able to do my identity law. Category left identity law, I wouldn't be surprised it's here as well, or something similar. No, the functor identity law, is it here as well? No, it's a little bit of functor identity law, here it is, you see, and so on. It's just using the laws that are available. So basically that's it. And by the way, I didn't write it in my README file, but and also not in the screencast. But there is a corollary that actually can relate, because it can relate two times this thing by composing with the mu, with the new. Remember, by tearing off one layer here as well. But if you really want the properties, it's a little bit. It's not really one correspondence, because somewhere you have to compose with new and then use one of those triple laws. But if you really want a correspondence which is similar to the one of the Yoneda lemma, you need to work with global values and these natural transformations. Okay, thanks.